videos will be posted tomorrow. When you see questions in our Slack channel that you also want to hear the answer to, please give it a thumbs up and we can go in order of votes. And there are many ways to clap, including the emoji. All right. Without further ado, our first speaker is Yao-Yuan Mao, who will be talking about exploring the data model and data access needs for simulated Rubin LSST datasets.
Thank you. So hi, everyone. I'm Yao. So I'm part of the Dark Energy Science Collaboration Desk. And as many of you know that in Desk, we are doing a data challenge too, which simulate Rubin LSST data. And so one of the question is, I mean, this is like a huge amount of work going from like embodied simulation all the way down to simulated LSST images. But one of the questions is, how do we deliver the data to about 900 plus desk members? And so in this 3 minutes, I'm going to talk about the work that we've been doing with a lot of desk members on creating a pipeline going from the DN science output to the catalog that people are using. And so on the right, you see a slide of this pipeline all the way go from embodied simulation to where the individual desk members access the data that we generated. Next slide, please. So I have not seen the next slide, but oops. Okay, so the main challenge here is how do we mimic a user experience that is similar to the future LSST science platform and a data model that's defined in the data product definition document, DPDD. And so we also need to anticipate a lot of change in the underlying data model and format at this point, right? Because the DN science pipeline has not been finalized. And so, I mean, every time we rerun it, some of the data model might change. The data output from the data science pipeline is also different from the data product definition document. So we also need to provide that translation to that. And so in Dust, we have developed this like abstract layer. It's actually similar to Boiler to some extent. So I demonstrate on the right, where you can see instead of using a database, we basically allow users to go through this abstract layer GCR catalogs to access the data on disk. And then in this Python package, GCR catalogs, we provide a translation to map the original DN outputs to the DPDD definition as close as possible. And by doing that, we can also mitigate some of the issue when the underlying data model is changing. Next slide. And so here, just on the right, I'm just showing you what the user will be doing when they try to access. They could define some query, specify the column they want to access, and then get a quantity. And then we are learning a lot of things from this exercise, like sometimes DPD is not sufficient for validation type of work. Like we need a lot of flag that was not defined in DPDD. And then extra care needed when we do interface with like additional Elan products. That's it.
Silvana, you're muted.
Yep. That was excellent timing, Yao. Thank you. Silvana, you found us. Great.
Hello. Okay, I'm going to start. And together with the team, we lead the Marte Research Project. Astronomers and people who have participated in NASA workshops and are involved. Aerospace contract to as many people as possible in a form of
Silvana, I don't know if we lost you. I can turn off her video, if that will help. No, that didn't work. What?
It can't hurt.
It didn't work, I think, because I think we've lost like internet access to her.
Okay, how about if she gets back online, we can return to her talk at the end. Skipping ahead. Our next speaker is Lucie Beaumont.
Hi, my name is Lucie Beaumont. I'm a PhD student at Stony Brook University, and my advisor is Anya van der Linden. And so I wanted to tell you a little bit about my project, which is weak lensing mass calibration of relaxed clusters. And so we calibrate X-ray masses of relaxed clusters in order to measure this quantity F-gas, which is the gas fraction of mass in a cluster. And so for relaxed and very large clusters, this quantity can give you some cosmology if you have priors on omega B. And so my data set is an LSST or Rubin precursor data set. It contains 21 clusters from DE cams to prime cam and mega prime. It's deep data. It's approximately 30 epochs, and we have 5 to 6 band photometry for each camera and 6 band photometry that's LSST-like for DE cam. Next slide, please. And so my work on this project includes development of 3 pipelines. So pixel level processing is done with the Tele pipeline developed by Thomas Urban in 2012. So I've added corrections for nonlinearity, crosstalk, the brighter fatter effect, and a stellar flat field. And then the second part of the pipeline is shear calibration and photoz's, and this is done with NGMix and Metacal. And so this has not been done for clusters before, so it's been kind of a learning opportunity. In addition, we use BPZ for photoz's. And then the third pipeline is a cosmology inference pipeline, and it uses Bayesian hierarchical methods. And what's notable about this pipeline is that we use the full redshift probability, the P of Z, instead of just the redshift point estimate for the clusters. Next slide. So this is some preliminary cosmological constraints that we have for just 10 subprime cam clusters with the P of Z masses and an older method of shear calibration. And we expect that the constraints on omega M by the end of this project will go down by about a factor of 2. So we're very excited for the results to come.
Thank you, Lucie. Silvana, we'll return to your talk after Xiaolong Li talks to us about preparing LSST for the detection of light echoes with AI.
Hi, so I'm Xiaolong Li, and I'm going to talk about my project about preparing LSST for the detection of light echoes. So the LSST will detect thousands of transients in the sky. The current data process pipeline is designed for point-like sources, but it will miss some diffusive features. One of such phenomena is the light echo. Next slide. So what is a light echo? Light echoes are the reflections of stellar explosions on interstellar dust. For example, supernovae and Nova and the Earth are at the 2 focal points of a 3D ellipsoid. Light from the supernova reflected off the dust that intersect the same ellipsoid surface will reach Earth at the same time. As time goes by, the ellipsoid expands, and what we see in the sky are beautiful circles coming later than their directly detected sources. And next slide. But most light echoes are more complex and don't have a circular shape because only a portion of the ellipsoid will have dust that reflects the light echo toward Earth. And on the right is an example from Atlas images. This is the light echo from supernova Tycho. Next slide. So why light echoes are important? Because it gives us a second opportunity to study transient by studying their spectra. And light echoes can be used to classify historical supernovae. And it also enables a three-dimensional view of an astronomical phenomenon. And it provides us invaluable information about dust. It reveals the dust structure around the transient. Next slide. But light echoes are extremely difficult to detect because light echoes are diverse and time varying. It's also very faint and diffusive, and there are a lot of false positives like the reflections of telescope and many other artifacts. The current ways to detect light echoes is by visual inspection of thousands of images from Atlas and the DCAM. And in the area of LST, the data volume will be 10 times larger. So, next slide. And data mining, we propose to use the AI to solve these addresses. So I will go through quickly. Next slide. The AI there are two main frameworks to detect object detection: the two-stage first sourcing and the YOLO. And the next slide, we try both of these Atlas images. We have totally about 1,000. We search over 46,000 fields and find totally 170 images. And we label two classes in each images. And the next slide. And these are the images from result from fast RCN and YOLO. Yeah, but there are some challenges. These four challenges are we will so address in the future. Yeah.
Thank you, Xiaolong.
Thank you.
Your turn. Okay, Silvana, we are ready for your talk.
Yeah, I'm really sorry. Hello again. Hello to everyone. I'm Silvana from Lima, Peru. And together with the team, we lead the Marte Equation Research Project. Astronomers and people who have participated in NASA workshops are involved. We wondered how to bring scientific knowledge, astronomy, and aerospace culture to as many as people as possible, in a form of communication that they can understand. Knowing that discoveries must be at the service of the population to help us develop as a species. Slide, please. Next slide, please. We spread the information about Rubin, other observatories, and workshops around the world, respecting the work of scientists and promoting learning. New platforms are ideal to spread knowledge in a friendly way. Sunday, yesterday, and today, we tagged Rubin and Instagram to test its level in duration. So we invite Rubin to have a funny conversation. We carry out scientific and social reports supported by research and sources in Peru and people in other countries. Slide, please. Thank you. So we have transferred the knowledge to a form of communication close to the bulk of the public using connectivity. And we have a work process that you can see on the screen that we follow to have quality control. If anyone in this extraordinary Rubin Observatory Break and Community Workshop 2020 wants to freely share the information in Peru, so you can do it from our platform. So we invite you to subscribe in our Instagram and YouTube channel. That is our break. Thank you. Gracias, desde Lima. Thank you.
Thank you.
Thank you to all our speakers. Eli, what questions do we have?
There is one question on the Slack channel from me to Lucie. I was just wondering what blinding you have in place there, because you were showing some cosmology.
Yeah, so this is a continuation of the Weighing the Giants Relaxed Clusters project. So we already had cluster masses for these 10 Subaru clusters. And we use, this is the cosmology results use the old X-ray data. So we have new X-ray data for additional clusters, including Perseus at low redshift. That's expected to really change the constraints on W. And we have also all new data from Megaprime and DECAM. So these cluster masses we're analyzing completely separately from the X-ray clusters. So we're blinding the cluster masses for the new data. So I guess the X-ray part and the lensing part are completely separate, except for the part that was old Weighing the Giants, but these had already been analyzed.
Okay. And so those plots you showed were for the old?
Yeah.
Okay, wonderful. So there are no other questions on Slack. If someone wants to chime in and ask any of our research biters. We have 6 minutes before we transition to the to another section. I don't know what we do if there's no more questions.
Yeah. Well, thank you to our 4 speakers. We will let you get on to your next research bite. Or actually, yeah, we'll let our audience member get on to our next research bite session while we swap roles and set up for the next half hour. Thank you, everybody, for joining.
Thank you all.
Thank you.
And I'm gonna, should I pause recording? Yes. I'm pausing recording. So, hello everybody, and welcome to session 2 of the Deep Imaging Techniques and Data Access. Yusra AlSayad and myself, Eli Rykoff, will be your chairs, and for this round, I will be keeping time with this handy toothbrush timer. And so you might hear the beep in the background when your time is up. And Yusra will be monitoring Slack for questions. And we have four flash talks. Please keep to 3 minutes each. And then 10 minutes of question and answer. And I'd like to very quickly remind you, you have agreed to the code of conduct, but we went through this already at the beginning of the session. And this meeting is being recorded, as the friendly Zoom lady reminded you. So first up, We have Yao-Yuan Mao on exploring data model and data access needs for simulated Rubin LSST datasets. And Yao, please take it away.
Thanks, Eli. Hi, I'm Yao. So I'm a member of the Dark Energy Science Collaboration Desk. And so as many of you know, that in desk we are doing a data challenge to simulate the Rubin LSST dataset. And so as the figure on the right shows, this effort goes all the way from embodied simulations, creating catalogs to simulate the images, and then do the LSST science pipeline processing. And here I'm going to highlight the latest part where after the LSST science pipeline processing, we then need to deliver this data set to about 900 desk members. And so I'm highlighting the effort that we are on this data access part and also the challenges we have seen. Next slide, please. So one of the main important aspects of this data access is that we want to mimic the user experience that people will be using when they access the LSST science platform and using the data in the data model defined in the data product definition document, DPDD. And we also have a challenge that the LSST science pipeline is not yet like fixed, right? So things could be changed as we run the pipeline. And so we need to allow enough flexibility for the user to access the data. And so to overcome these issues, instead of using a database, we develop a Python package to serve as an abstract layer. So to some sense, it's a little bit similar to the bottler, for those who are familiar with it. And basically, as the diagram show on the right top, instead of using a database, we allow the people to use this Python package to access the raw data on disk directly. And then within this Python package, we define several modifiers to translate the column data models in the LSST science pipeline outputs to the final DPDD as close as possible. And so then people can then access the data as if those have a DPDD definition. Next slide. And so with that, we create this desk science platform basically at NERSC using Jupyter Hub. So similar to what people will be using as the LSST science platform. And so on the top right, you can see a snapshot of how people will be accessing the data. Like you can define some query and then specify the column you want to access and then grab the data. And then so a few particular challenge that I want to highlight is that, for example, we found that the DPDD is usually not sufficient for validation work because a lot of time you need to access certain flags that are not defined in DPDD. We also found that we need particular care if we want to join our data product with like additional add-on product like PhotoZs and things like that. We are also exploring some other different access methods. Thank you.
Perfect timing. Thank you very much, Yao. So now we have Silvana Acco Carbajal. And Silvana, you can unmute yourself and please take it away.
Yeah. Hello.
Hello.
Hello to everyone. Yeah. Yeah. Hello to everyone. I'm Silvana Acco from Lima, Peru. And together with the team, we lead the Beaumont research project. Astronomers and people who have participated in NASA workshops are involved.
Silvana, losing audio. If you could turn off your video, that might help.
Hello.
Silvana, are you there?
Yes. Can you listen to me?
Yeah, I can hear you now.
Yeah, okay, thank you. So we wondered how to bring scientific knowledge, astronomy, or aerospace culture to as many people as possible in a form of communication that they can understand, knowing that discoveries must be at the service of the population and help us to develop as a species. So please. We spread information about Rubin, other observatories, and workshops around the world, respecting the work of scientists and promoting learning. New platforms are eager to spread knowledge in a friendly way. Sunday, yesterday, and today, we tasked Rubin on Instagram to test its level of interaction. So we invite Rubin to have a funny conversation. We carry out scientific and social reports, support the research in sources in Peru and people in other countries. Slide, please. Slide, please. Thank you. We have transferred the event to a form of communication close to the bulk of the public using connectivity. And we have to work process that you can see on the screen that we follow to have quality content. So if anyone in this Rubin Observatory project and Community Workshop 2020 wants to freely share their information in Peru, you can do it without our platform. So we invite you to subscribe in our Instagram and YouTube channel. Thank you and muchas gracias desde Lima.
Thank you very much. That was right on time. So thank you, Silvana. Next, we have Lucie Beaumont on weak lensing mass calibration of relaxed clusters. Take it away, Lucie.
Hi, my name is Lucie Beaumont. I'm a PhD student from Stony Brook University, and my advisor is Anja van der Linden. So my project is to work on weak lensing mass calibration of relaxed clusters, and the application of this is towards the F-gas measurement. So this tells you the mass fraction of gas in a galaxy cluster, and because clusters condense from such large portions of the early universe, you can say that their matter content is representative of that on cosmological scales. And so by measuring F-gas, you can then constrain cosmology. And so my measurement is the weak lensing measurement, which constrains M total, and M gas is measured from X-rays. And so our data set contains 40 X-ray clusters from Chandra and XMM, and then an additional 21 clusters in the optical from DE-CAM, SuPrime-CAM, and MegaPrime. And so this is all Rubin precursor data. It's deep, approximately 30 epochs, which we can compare to approximately 100 epochs of LSST or Rubin 10-year depth. And it also has 5 to 6 band photometry. And in DE-CAM, it has the LSST filters, U, G, R, I, Z, and Y. Next slide, please. And so this project involves 3 different pipelines. So the first pipeline is pixel level processing. And so I've adapted the tele pipeline from Thomas Urban to work with DE-CAM. And so this includes new corrections for nonlinearity, crosstalk, the brighter fatter effect, and a stellar flat field. The next part of the pipeline is shear calibration and photoz's. And so for shear calibration, we are using a combination of NGMix and Medi-Cal. And for photoz's, we're using BPZ. And all of this is fed into a cosmology inference pipeline, which is a Bayesian hierarchical pipeline. And this pipeline makes use of the P of Z method. So we use the full redshift probability given from BPZ instead of just a point estimator. And this method is unbiased. So next slide, please. We have some preliminary cosmological constraints. These constraints are from our cosmology pipeline, but they're only with 10 SuPrime-CAM clusters instead of the full 21 clusters, and an old shear calibration method. In addition, we have a few more X-ray clusters, including a low redshift cluster that will definitely change the dark energy constraints. So by the end of this project, we expect omega M to decrease by approximately a factor of 2.
Thank you very much, right on time. And let me see. Next, we have Xiaolong Li on, preparing LSST for the detection of light echoes with AI. So please take it away.
Hi everyone, I'm Xiaolong and from University of Delaware. So the LST will detect thousands of transients in the sky, and the current data process pipeline is designed for points-like sources, but not for diffusive features. One of diffusive features it will miss is the light echoes. So next slide. So what is light echo? Light echoes are the reflections of stellar explosions on interstellar dust. For example, a supernova and the Earth are at two focal points over 3D ellipsoid, and light from the supernova will reflected off dust that intersect the same ellipsoid come to the Earth at the same time. And what we see on the sky is the beautiful rain coming later than they are directly detected sources. So next slide. But most light echoes are more complex and don't have a circular shape because only a portion of the ellipsoid will have dust that reflects the light toward Earth. Next slide. And why light echoes are important because it gives us a second opportunity to study transient and enable three-dimensional view of an astronomical phenomena. And it also provides invaluable information about dust. So next slide. Light echoes are extremely difficult to detect because they are diverse, time varying, faint, and diffusive, and there are lots of false positives like the reflections from telescope and many other artifacts. And in the area of LSST, the data volume will be 10 times larger, and data mining techniques are needed for detecting light echoes. The current state ways to visual inspection thousands of different images will be impossible for LSST. So next slide, and next. And we propose to use AI to address this problem. One of the most basic unit of AI is convolutional neural networks, which has proven to be very successful in learning features from images such as edges, shapes, and so on. And the next slide. And the object detection framework, the FORSTER, RCN, and YOLO has reached real-time human-level performance. In performance, we try those two models to detect light echoes. Next slide. Our dataset is from Atlas telescope. It contains 34 different fields and the totally 170 images. We trained these images on FASTAR, Xiaolong, and YOLO. And next slide. And in each image, we label two classes, the star and the light echoes. And next slide, you will see the result from FASTAR, Xiaolong, and YOLO. Both models can meet human level performance. Next slide. But there are some challenges. The first is the class imbalance problem. Number of stars are much larger than light echoes. The second, we cannot label the light echoes at all signal to noise ratio just by visual inspection. And the third is the limited training data. Overfitting on current dataset will lead to missing new light echoes. To solve the third problem, we have to find ways to create diverse light echo images. And those are the problems we are going to address in the future work. Thank you.
Thank you very much. Yusra, any questions?
Thanks, everybody. Our first question is from Sir Hoodmore for Yao. Sir Hood, do you want to unmute and ask?
Yeah, sure. Hi, Yao. I wanted to ask about the access that you provide from these GCR catalog readers. So the access to the disk, is that like a parallel access or a serial access?
Thanks, Sue. So the abstract layer does support data partitioning. So whether or not you can actually do a parallel depends on the underlying file format. If you can switch to the next slide, if the underlying file are partitioned into several files, then yes, then you can do it. Like you can read in parallelly on different nodes. But if the underlying is only one file, you can still do it parallelly, but then you're still limited by the I/O. And since it's only abstract layer, there is no additional magic to make things faster.
Right, yeah, sure. So what I was envisioning is whether this raw data that you say on disk, is this something which is going to be the LSST data access or database, or is this something that you may want to create a new thing? Because in case you need a parallel access, and then as you said, you need to partition it appropriately, right? So
yeah,
is this something that you're
example,
thinking about, or?
Right, so for like object catalog, for example, we do save track by track, since that is the most logical partitioning.
Right.
And so to that extent, then if you use desk, for example, and then we save it in Parquet format. And so you can use desk to do like some kind of parallel access to multiple tracks.
Right.
But no, we are not like the raw data format. We don't know if that will be the same format as what the LSST provides.
Great, thanks.
There is another question for Yao. John Swinbank, would you like to ask?
Sure. So I think you possibly kind of actually already at least partially answered this in the answer you just gave, but it was not immediately clear to me, and I possibly missed it, whether your normalization step was happening once and then you were storing the normalized data, or whether you were doing normalization from the raw on effectively every query or every update. And if it's the latter, I think it was the latter, how does that work in terms of scalability? If the normalization code gets complex, can the whole thing just slow down?
Right, great, thanks. Yeah, so it is done on the fly as you load the data each time. The performance wasn't too bad because NumPy array operation is really fast. And so we don't see performance, like that is not a limiting factor at all. I mean, we do, at some point we was like thinking maybe we can do like Milky Way dust extinction on the fly, and then we decided not to do that. So yes, if you have like very complex on the fly calculation, it will still slow down. But for like unit conversion, something like that, it won't be an issue. But also after translation, we are also trying to save the after translation data into a new file. And so that is a different attempt that we are trying to save, not just the raw data, but also the DPD, the final product. And we were exploring with alternative SS methods so that like in the final DPDD format. So in those cases, then there's no performance issue.
Sure. Thank you.
And I should add, as a user of these, once things, it's a generic on top of all sorts of things, but if it's backed by the Parquet files, then things run a lot better than before when it was backed by HDF5 or any other kind of files. So.
Thanks, Yao. Our next question is from KT for Xiaolong.
Okay, well, it's been answered in Slack, but I'll ask it anyway for the record. And I was just whether you're using the time domain evolution of the light echo, since there are many now time domain neural networks, or are you using only single epochs?
Currently, I use only single epochs, but we have five images of 5 epochs for each light echoes. We may consider time evolution of light echoes in the future.
Thank you.
Thank you. I don't see any more questions in Slack, but if you would like to ask a question of any of our speakers, please use the hand raise feature on Zoom right now. Going.
I think
Okay.
there's a question on the chat.
Oh, I see. Okay, question from Matthew Rumor for Silvana. Is there a target audience or a specific use case for the platforms you're developing? And are you involved with the CET?
Hello? Yes. This is for everybody and especially for young people. Can you listen to me?
Yes,
Hello?
we can hear you. Yes, we heard you say that the target audience is young people.
For everybody and young people, yes.
Matthew, I don't know what the CET is.
That would be the community engagement team. Which is part of the Rubin operations organization that we heard about this morning.
Silvana, are you involved with the community engagement team?
Or I might also ask, I mean, if you're targeting specifically young people, then perhaps the education and public outreach team as well, which Federica has also said.
Anything else?
Are there any more on chat? I haven't.
Lucie, perhaps I missed it, but is there any chance that you can, sorry, is it okay if I just ask the question?
Yes.
I'm gonna go ahead. Perhaps I missed it, but is there any plan on running this pipeline on simulated simulated desk images that we heard about today? The validation images and the directly on the science platform.
So I think the general plan is to try to run the shear calibration pipeline on simulated images, just because NGMix and Medi-Cal has not been run on clusters before. And so to understand what happens as you go to higher shear, and also what happens when you have additional blending, and how to best take advantage of the kind of fitting that NGMix has. This is a project we'd like to do in the future. I think right now the amount of uncertainty that it would reduce is just subdominant, but we do plan on doing this.
Thank you.